Lesson 1.6, Infinite Geometric Series. You've heard a lot about arithmetic and geometric sequences and series. So now we're adding just one more word to the picture, and it changes what we're doing by just a little bit. And it's that word, infinite. Now, we've seen this already. I think it was back in 1.1. Infinite, meaning the number infinity, which means going on forever. It has an infinite number of terms. It can keep going. There is never any end, which we can do for geometric sequences and series because we just keep multiplying by the same number over and over. And even if they get really close to zero, they don't actually become zero because we're not multiplying by zero. So we've got two different types of series. Again, we've already heard about these, but just to recap, we have convergent series, which means that we're going to have an infinite number of terms, but when we continuously add terms and then sum those values together, they approach a fixed value. Now, quite often, this number is going to be relatively small, but it literally could be any number. It could be 1, it could be 2, it could be 10, it could be 1,000. But it needs to be a fixed value. You need to be able to predict that it's getting closer and closer to a specific number. So the example we have here is 1 plus a half plus a quarter plus an eighth. If we actually did some math with that, we would see that the sum of our first two terms would be 1 1/2. The sum of our first three terms would be 1 3/4. The sum of our first four terms would be 1 7/8. And so we can say that this is approaching divergent series on the other hand. Again, not the book. Okay, so we're not going to be watching a movie about divergent series in this class. It's a series with an infinite number of terms. So again, we're seeing in both of these, they are infinite geometric series. But divergent series means that the sequence, when we add them all up together, all those different terms, they are not coming to a fixed value. They are forever changing in terms of what that number is. So if we do the same sort of steps as we did for example 1, we take the sum of the first two terms, that's going to be 6. The sum of the first three terms is 14, and the sum of the first four terms is going to be 30. Well, these numbers are not getting closer together. They are getting farther and farther apart, which means it is divergent. It's diverging, it's spreading out, it's getting bigger differences between each sum. So who cares? What does it matter? Well, what happens is that when you get to the sum of infinity, we can actually determine what that is if the series is converging. If it's not, it's going to keep going forever. It's getting bigger and bigger, so it could keep getting bigger and bigger forever. So the sum would be infinity to some greater or lesser extent. In general, we say that the sum of an infinite geometric series, specifically when your common ratio is between -1 and 1, then you can actually figure out the infinite sum or the infinite geometric series by using this equation. And again, notice we are having another equation. Looks kind of like the previous geometric series equation that we had, but it's not quite the same. So I'll write them beside each other just so you can have a reference. And there you have it. So we've got some similarities. We've got term 1 in the numerator. We've got 1 subtract our common ratio in the denominator. We're just losing that piece where we've got our 1 subtract our common ratio to the power of n, because now n is infinity. All right, so let's try some examples. We've got example number 1, determine whether each infinite geometric series converges or diverges. If it converges, determine its sum. So the first thing we're having to figure out is it actually converging? So we can test it out. First two are adding up to 40, then we've got 42, then 42.5. So we can test it that way just by strictly checking our sums as we increase the number of terms, or we can determine our R value. So that's term 2 divided by term 1. So 8 over 32, which gives us 1/4, or 0.25. No matter which way you want to look at it, that is the direction it's going. It's getting smaller. We go back to that initial definition. I'm going to just zoom out a little bit so you can see it at the same time, where our common ratio is between -1 and 1. That is definitely the case here. So it is converging. So since it converges, we can use our formula. Sum of infinity equals term 1 divided by 1 subtract r, which means that it's going to be 32 divided by 1 subtract. And we can do a fraction or a decimal. I prefer fractions because then I can keep with my mental math. So that's 32 divided by 3/4. Dividing by a fraction is like multiplying by the reciprocal. So that's 32 multiplied by 4/3. From here, that might give me a little bit of a large number to work with. So if I use a calculator, I'm going to get 42.6 repeating. Or if I don't use a calculator, or maybe I want to keep it in fraction form because I'm looking for an exact value, something that I can continue to work with, then I'm going to go just 32 multiplied by 4. And that is something I can do in my head. It's going to be 128 over 3. And so those, either one, are my solution for part A. Now, number 1B, first thing we need to do, check to see if it converges. I'm going to calculate using my common ratio again. So I'm going to do term 2 divided by term 1. So -10 divided by 100 is -0.1, or -1/10. Again, fractions versus decimals, that's your choice. That is between -1 and +1. Therefore, this also converges. So, my infinite geometric series, oh my goodness, why are you doing this? Term 1. 1 minus r is my denominator. Got 100 divided by 1, subtract -1/10. Again, watch out for those negatives. You want to make sure you put brackets around them so that you don't accidentally drop it entirely. Got 100 divided by, or 11/10. Multiply by the reciprocal. And we have 1,011ths, or if you really don't like the way that looks, because it's a little bit monstrous, you divide 1,000 by 11, and you get 90.9. Either way, you are now dealing with a value that you're going to be approaching for this whole sequence. So even if you go to the 20th term, you're not going to go past that 90.9. Continuing with examples, check our R value. We've got -1/3 divided by 1 is -1/3. This is, therefore, it does converge. because it's between -1 and 1. Again, getting in the habit of writing that equation every time is a big part of it. So we've got 1 divided by 1, subtract -1/3. So we add positive when we're subtracting a negative. Those terms cancel out. So we've got 1 divided by 1 1/3, or 4/3. Multiply by the reciprocal, and we end up quarters because we're multiplying by 1. So that one actually gives us a nicer number, even though usually -1/3 leads to terrible things in math. At this point, you potentially noticed that in the last 3 questions, we ended up with some sort of fraction in our sequence. In this particular case, it jumps out at me that we already don't have any fractions, and that my numbers are increasing each time by a greater amount. Still going to check my R value though before I even think about deciding is it diverging or converging. So -4 divided by 2 is -2, which is diverging, not digesting, because it is greater than, or actually technically it's less than, -1. So it's outside those parameters of between -1 and +1. Therefore, we cannot figure out the sum of the infinite series. The last example for this lesson is to work somewhat backwards. So this asks, determine a fraction that is equal to 0.49 repeating. So we know common repeating fractions, like 1/3 is always 0.3 repeating, and 2/3 is always 0.6 repeating. We get into 11ths and we get repeating decimals, but this one isn't actually one of our common ones, so we've got to think about it a little bit. Specifically, how does this fit in with our current topic? Well, let's break it down. 0.49 repeating can also be written like this, which means all of these guys are their own, we could be breaking it apart into their own separate pieces. Also looking at it as 0.4 plus 0.09 plus 0.009 plus 0.0009, and all of a sudden, do we see a pattern coming up? Absolutely. We've got one more 0 in there every time. Moving place value is a geometric series. So ignoring the 4, because that kind of doesn't fit the pattern, we could maybe figure out what fraction is relevant to our 9s. Maybe that'll help us out. So we start just like before. Figure out your common ratio. 0.009 divided by 0.09. And we get 0.1 or 1/10, depending on which way you want to think about it. I'll use the decimal this time, just so that we see it both ways, because tenths are actually easy to work with. From there, the sum of infinity, or infinite terms, we've got 0.09 divided by 1 minus 0.1. And again, this is filling in our original formula. And we calculate this to be 0.09 divided by 0.9, which is also 1/10. So all of this piece, starting from 0.09 to 0.0009 and so forth, That is all going to end up adding to 1/10, because I got 0.1 from my calculator again. But don't forget, we ignored this guy at the beginning of the question because it didn't fit our series. So we need to add that back in because it's part of this decimal too. And so what we get is 0.4 as a fraction is 4/10. 0.09 plus 0.009 plus 0.0009 is equal to 1/10. So we are adding that together. And so our fraction is 1/2. So even though it's technically not 0.5, because those 9s continue infinitely, when we added them all together, they would end up equaling approximately 1/10. That's what they're approaching. And so we add that to the 4/10 we already had. We get 5/10 reduced to 1/2. And that is my answer. So in and of itself, this concept is not the craziest piece we've had. We only had one formula, and there's not a whole lot of working backwards, working forwards through it. Kind of nice because you're only ever dealing with term 1 and R both only appearing twice. So what you need to do now is do some homework. So 1.6 extra practice is in your notes package. And also you've got page 68 to 73 in your workbook. Don't forget, you can always check in the inside cover of your notes booklet to find out which questions exactly you should be working on. The great news is that once you're done all that homework, you are ready for your second assessment.